Hello and welcome back to the course on artificial intelligence. Previously, we had quite a strenuous and long tutorial on markov decision processes, and hopefully you got along well with that, and hopefully I could explain things in a approachable and engaging way. And today we're going to talk about policies versus plans. It's going to be a quick and fun tutorial because now we're entering into a new world. We're entering into a world of stochastic search, non-deterministic search. It's not just about getting through the maze, but also accounting for random factors that might just hit you in the head when you're going through this maze, and you need to be prepared for them. That's the world our agent is living in, and it's more fun, but it's also more dangerous. It's less predictable. So how is our agent going to behave? Let's have a look. There's our Markov decision process framework, which is once again our favorite Bellman equation. However, the more advanced version of the Bellman equation we were working with. So from now on, we're just going to call this the Bellman equation. And here we've got our maximum across all actions. So the value of a state, any state S, is the maximum across all actions that an agent can possibly perform in that state. And the maximum was taken from the reward that the agent will get by performing action A in state S plus a discount factor multiplied by the expected value of the new state it will be in. And the expected value is taken here because it doesn't know exactly what state it'll end up in. There are some random effects that are present in the environment that might alter the state, and he might not end up in the desired state. He might end up in a different state. That's why we're taking the expected value over here, this sum over here. So let's have a look at this as our example, or in our example of the maze. So this is what we had previously. So previously we were dealing with deterministic search. So we knew that, all right, so if I'm here, I definitely need to go here. If I'm here, I definitely need to go here. If I'm here, I definitely need to go here. If I'm here, I'm here. So it was all pretty straightforward. Once you have this map, and remember we called it a plan. Once you have the plan, it's pretty straightforward what you need to do. There are our arrows. So that's the plan with the arrows. And from here it was very straightforward. These are the routes that the agent would take. Wherever you start on this blue line, that's exactly the way you would go. However, now we don't have a plan anymore. We can't have a plan because whatever we plan might not happen. It's not under our control. A plan is when you know exactly what you need to do next. You know the steps. So you have a starting point, you have a goal, and you know every single step, so you can plan them out. You're like, I'll do this one, I'll do this one, I'll do this one, like in life, like a plan. But at the same time, there's so much now randomness going on. You can't have a plan because what if you get here and then you click to the right and actually takes you down? So that's not part of your plan. So that's why it's not called a plan anymore. And here we're going to calculate the values, or we're actually going to just look at the calculated values for this same problem, but given that we have this randomness inside. So these are the new values. And so why are these values different? So let's just compare it to what we had previously. This is what we had previously. These are the new values. So once again, we had previously, you can see 1, 0.9, 0.81, 73, 66. And this is what we have now, 86, so less than 1, 74, 71, 63, and so on. And by the way, these are not exactly the correct values. These are off the top of my head, but if we were to run an agent, some values would be something similar to this. And the values could change because depending on the gamma that we choose, 0.9 or other value. But nevertheless, for argument's sake, these are the values that we're dealing with now. And they're approximate. They convey the whole notion in the correct way. So let's have a look at them. Why have they changed? Well, let's start with this one. Here the value was 1. Why is it all of a sudden 0.86? Why is it less than 1? Can't we just go from here? Well, we actually can't, because from here, if we go right, which is our intention, if we go right, we would actually, with a 10% chance, we'd end up here. So we'd hit the wall and we'd be back in this state. And remember, we have a gamma, so the value would be discounted. Or with a 10% chance we would end up here in this state. So it's not 100% probability I would get here. So therefore, this value can no longer be a 1. It's something less. And let's say it's 0.86. So that's an example of why it's like this. And you could get exact value if you calculated the Bellman equation, the full Bellman equation that we have now. The only problem is that there'd be some recursion because you would need to know the value for this, and then you would need to know the value for this. It's quite complex, and that's why we're not doing the calculations manually here. That's why but the AI can do them as it's going through all of this. It's like nothing too complex for the AI to calculate these things. So that's our value here, but now let's take a look at a different one. So here it used to be 0.9 just because of the discounting factor, remember, from here to here. Again, now from here, we can't just jump from here to here simply because even if we jump, if we go like this, we might end up back here, right? There's 20% chance that we'll still stay in the square because we'll hit a wall. And again, and so on. So the value of being here is 0.71. Again, the discounting factor, this might look odd to you that this is, even with the discounting factor, this is too high. Maybe the discounting factor in this example is not 0.9, maybe it's 0.99 or something like that. So don't worry about that. Just kind of like focus on that the values have indeed changed, that the values are now less, mostly because it's not 100% probability to get to the state that you want to get. And what you will find an interesting one is here, that here it used to be 0.9 and it actually has dropped very much. It's dropped substantially. Why is that? Well, because if you go from here up, which is our intention, there's a 10% chance of hitting the wall, but there's a 10% chance of actually ending up in the fire pit and losing -1 to your reward. And basically that means for the agent, that's end of the game. And so this is a very bad state to be in. So all of a sudden, remember, we had 0.9 here, 0.9. So they were equivalent. It doesn't matter you here or here. They're pretty much equal in terms of value of being in each of these states. But now all of a sudden, bam, this state is like nearly twice as good as this one, simply just because here, if you go straight to, you go right where you want to go, the consequences of the randomness occurring is you just stay here. Here, one of the consequences, the 10% chance, is you end up in the pit. So as you can see, this is no longer such a good state anymore, simply because of something, that fluctuation that could happen. As you can see, this one is also very bad because it's as bad as this one in terms of, there's only a 10% chance of ending up in the pit and 10% chance of ending up in the wall. But at the same time, there's the discounting factor. So first of all, the discounting factor, and also after this one, you'd have to go here. And even if you hypothetically went here, you could end up in the pit again. So that chance would also be taken into account, because remember, this value is derived from this value and this value is derived from this value, right? And therefore it's smaller. But in reality, actually, that what I said there was wrong. This value is not derived from this value. So if you just have a look now, you will notice that this value, V over here, is actually greater than this one. You will notice that for the agent, it's better to go around this way than this way. And it makes sense, right? Because this way, it doesn't lose. There's no chance of getting in the pit. Yes, it's a bit longer, and therefore the discounting factor has a bigger effect. But at the same time, simply because there's a chance of getting in the pit here, if it goes straight, there's a chance of it jumping in the pit. So it'd rather take its time, and it'll just like go around, because that way there's a much lesser chance of it getting a pit. There still is. So if from here it goes there, if from here it goes there, it could potentially get into the pit, because it could end up there and then it could end up in the pit. But nevertheless, it's a lesser chance, so it would just go around like that. So very interesting to see how the route changed. Remember, previously from here you would go like that, from here you'd go like that, and from here you'd go like that. And now all of a sudden you can see it's changed. So let's draw the arrows and see what it looks like now. And oh, voila, you see even a more random thing, right? So yes, this is true, but look at what happened here. Look at this one, and look at this one. Were you expecting that? That's something definitely, like when I saw this for the first time, I was very impressed. I was not surprised. I was surprised, and I was not expecting this at all. And this is an example of, when AI can outsmart a human. It's like something you can't even predict, but the AI, through reinforcement learning, remember that example of the dogs that can actually sometimes walk better than normal real life dogs, or pre-programmed robot dogs, or can play soccer, simply because they come up with these ideas that even we can't see. And so that's a great example, right? So you probably weren't expecting that as well, that the agent, instead of going up, it's like, why would if I go up, then there's a 10% chance I'll jump into the pit. But what does it achieve by going into the wall? Well, 80% of the time it'll bump back and stay in this state, but 10% of the time it'll go here, and 10% of the time it'll go here. So all of a sudden you can see that Now it's actually in this new approach of jumping into the wall, there is a 0% chance it will go into the fire pit from this spot. So, and it's like, it really doesn't want to go into the fire pit. So it rather bounce into the wall a couple of times, and then it will go either right or left at some point, because that randomness is going to happen. And so it learned that through experimentation. It learned that, okay, when I go forward, the results are not as good as when I go to the wall. And if you think about it, it's like this robot. If you think about it, like there's a fire pit, this square is like a very tiny ledge, and then this is like a mountain, like a cliff, and this robot is just hugging the cliff and just, like trying to waiting until it like pushes it right or left. Because, well, as a human, you'd probably do the same. You wouldn't be standing facing that way or that way. You'd be hugging the cliff, right, or something like that. And hopefully you never end up in a situation like that. But like visually, if you think about it, same thing here. And so that's pretty intense, right? So that the AI came up with this idea. And same here, that instead of going left and risking getting a fire pit, I'm just going to try bounce off the wall, like, hug the wall, try to jump into the wall. And at some point I know that, just there's a probability, there's a 10% chance every time I do that, I'll go here and sometimes it will happen and I'll end up here and I'll be safe. And then I'll just keep going like that. So very, very interesting approach that the AI took here. And as you can see, the routes are like this. So from here, it might go right and then it'll go right to the exit, or here it'll go left like that. And here it will, at some point, it will go left and it'll go like that. Again, this is important to understand. It's not a policy. So even when it jumps from here, it will go here, maybe, and then from here it might actually, instead of going straight, it might actually go back to the right, and then from here it might go to the left, it might go to the right. So there's lots of different options for it to go. So it might not follow exactly this arrow, it might go the other way. This is just the desired routes that it's designed for itself, but the way it'll work out is actually could be different. It depends on the real world. So there we go. That's the world of artificial intelligence. That's what a policy versus a plan is. And hopefully you're slowly getting excited by what the AI can do, especially given what we saw over here. These are some very virtuoso type of decisions that the AI is coming up with. And as you can see, when you apply AI, even from this small example, you can see that even when you apply AI in the real world, maybe you'll come up with ideas and decisions that even sometimes humans can't come up with. And that's exactly kind of like what happened in those games where the Google AlphaGo was playing versus Lee Sedol, the champion of Go in Korea, back in the world champion of Go, and they were playing in Korea back in 2016. I think it was March 2016. It came up with some moves that humans had never played in 3,000 years, or humans were not used to playing. And this is exactly an example of that. So once again, hope you're getting excited and pumped about this course and about what we're going to create. And I look forward to seeing you next time. Until then, enjoy AI. Hello and welcome back to the course on artificial intelligence. Today we're talking about the living penalty. All right, so here we've got our Bellman equation, and as we've been going through this course, we've been slowly making it more and more complex. So far we've already added these probabilities in here, and also we've added the discounting factor. Now we're going to look in more detail at this side of the equation where we have the reward. Now remember previously when we talked about how reinforcement learning works, we said we have an agent and it performs actions in the environment, and in exchange, or as a result of that, it gets a new state in which it's now in and a reward for that action. Well, so far in our example, we've only been getting rewards at the very end, either if we get to the finish line, or if the agent ends up in the fire pit, he gets a +1 or a -1 reward. But that is a very simplistic approach to reinforcement learning, and in more realistic scenarios, you will likely have rewards throughout the journey, not just at the very end. You might have rewards throughout the journey. For instance, if it's an AI playing a game, and if, for example, it's like shooting somebody in Doom, it might get points for killing that enemy. Or it might be in a different other game, if it overtakes another car or something like that, just because of the rules of the game, not because of its way of analyzing the game, but actually the game is structured in a way that it's reinforcing, it's giving points for doing certain actions even before the game is over. So scenarios like that are very common, not just in games and also in real life. And that's why we're going to introduce something similar into our example, a simplified version of that, but nevertheless a reward that is continuously given to the agent throughout the game, not just at the end. And the way we're going to do it is by looking at the other tiles. So right now we only have reward +1 at the final tile and reward -1 at the other final tile, the fire pit. But now we're going to add rewards in every single tile. We'll add a very small reward. It'll be -0.04, and as you can see, it's negative. So every time the agent moves, he'll get a negative reward. And that's why it's called a living penalty, because no matter where he goes, he will always get this negative reward, except for these final tiles, because that's the end of the game. And so here you can see the reward even on this tile is -0.04, but that doesn't mean that he starts with that reward. He only gets this reward, and this is important to remember, he only gets this reward when he enters a tile. So whenever he performs an action, he goes here, then he will get this reward -0.04. And then if he comes back to this tile, he'll get another -0.04 reward. And so the longer he walks around, the more he accumulates this negative reward. And therefore, it is an incentive for him to finish the game earlier, as quickly as possible. And so now let's have a look at how our policy, or how the agent's policy, is going to change depending on what value we set for this reward. So here are 4 environments, and in each one we're going to explore a different reward. Now we're not going to do the calculations, we're just going to project the results, and you will see that intuitively they make total sense. So here we've got a reward for any step, or for getting into any state, is equal to 0, just as what we've seen before. Here the reward is going to be -0.04, what we just introduced now. Here the reward will be -0.5, or the living penalty will be -0.5, so much higher, you can see, than here, more than 10 times greater. And here the living penalty will be -2, so even more than the reward you get for jumping, or even less than the reward that you or the agent gets for ending up in the fire pit. So let's have a look at how the actions, or the optimal policy for passing this environment will change depending on this reward. So this is our original policy. And as you can remember, we had these 2 very interesting and even a little bit weird decisions by the agent, but which totally makes sense if he can live for as long as he likes, if he can just travel around for as long as he wants without being penalized for staying alive very long. Why not? Why wouldn't he just go into the corner here, into the wall, and just keep doing that until it so happens that he goes this way, and then he will walk around. And same thing here. It's much safer for him to jump into the wall, hoping that one of these will come up eventually, and then he'll go to the finish line anyway. Because by choosing these 2 actions, he doesn't risk getting into the fire pit. Now let's see what happens if we add a reward, a negative reward for just being alive, for making a step, for making a move. So here you can see that instantly these 2 changed. Now the agent doesn't want to jump into the wall. He is more likely to risk getting to the fire pit, having a 10% chance of jumping in here, but he will go forward. Because every time he jumps into the wall here, if he was going to be doing it here as well, every time he jumps into a wall, he performs an action, he ends up in this state with an 80% chance, and that means with an 80% chance he will get a -0.04 reward, meaning that a lot of the time he's going to be getting this, accumulating this negative reward. Same thing here. If he jumps into the wall, waiting for that moment when he will actually be randomly moved to the right, if he keeps doing that, he will accumulate this negative reward, and that the result of that, if you perform the calculations, you'll see that the result of that, the expected value of that approach, jumping to the wall, is worse than taking the risk of going forward and actually ending up in the fire pit. So he changes his decisions in these 2 blocks to instead move forward, and here move to the left, even though there's a risk of jumping in the fire pit, simply because now the longer he's alive, the longer he will accumulate this living penalty. In the next environment, now we're increasing the living penalty to even a greater number, -0.5, and let's see what changes here. So now you can see that compared to this environment, the only thing that changed here is that this arrow is pointing to the right. And what that means is that now it's no longer a good option for the agent. Oh, actually also this arrow was pointing to the left, and now it's pointing to the upwards. So now it's no longer a good idea for the agent to go around from here, go around all the way, because if he goes around all the way, yes, he's safer. There's a lesser chance. There's no chance of getting into the fire pit. But at the same time, or there's a less chance of getting to the fire pit, but at the same time, he will accumulate quite a substantial negative reward as he walks around. So the path is too long. So that forces him, even whether he's here or here, to take the shorter route to get here, even though he has a much higher risk of getting into the fire pit, because as soon as he ends up in the square, there's a 10% chance of getting into the fire pit. According to his calculations, it's just the expected value of this approach is better than the expected value of going around, simply because we've increased this living penalty. And finally, we're getting to the example with the living penalty of minus 2.0. So here, I would encourage you to pause the video now that you've seen how the policy has changed as we increase the living penalty. I encourage you to pause the video and to think for yourself, what will happen in this scenario? What do you think the optimal policy will be, given that the living penalty is so high? So I'll let you pause the video if you'd like to. And now I'm going to jump into showing you the solution. So in this case, if you increase the penalty to minus 2.0, it's so high. Remember that the penalty here is only minus 1.0. It's so high that the agent just wants to get out of the game in any way possible. Even if it's just by jumping into the fire pit, he will do it. He will be like, every time I make a step, every time I end up in a new state, or every time I make an action, I end up getting a minus 2 reward. So what's the point of trying to get to the finish line if from here it'll take me 2 extra steps? I'm just going to go here and then straight into the fire pit, because that way my reward is going to be less. The negative reward is not going to be as bad as in the case of just making additional steps. So you can see that adding this living reward, and depending on the value of the living reward that we're adding, the results are going to be different, and the agent is going to select different policies. And that's basically how the reward value is incorporated by the Bellman equation, even when it's not just at the finish line or at the end of the game, but even throughout the game. And once again, it doesn't have to be on in every single state. Depending on the environment itself, it might be given to the agent at certain specific states, not at every state. But in our simplistic example, we're just using rewards at every given state to illustrate this concept. So I hope you enjoyed today's tutorial. And as you can see, we've already made our Bellman equation quite sophisticated, and now it can be applied to many different scenarios. And I can't wait to see you in the next tutorial. And until then, enjoy AI.